Hi, I'm Saurabh and I'm presenting our work on OOElala, Order of Evaluation based alias analysis for compiler optimization. This joint work with Ankush Phulia and Weber Bhagi at IIT Delhi. This talk is about expressions in C and their evaluation. Expressions in C may have side effects. Consider this expression I equals minus minus j plus k. While this expression computes a value, it also involves two side effects, one on object j and another on object I. These side effects may be applied in either order and at non-deterministic times during the evaluation of this expression. Thus, the order of evaluation or OOE of operands in an expression is often unspecified. Consider the first expression plus plus I plus j minus minus. The side effect induced by j minus minus may occur before or after the increment of I. In fact, the two side effects may proceed in parallel. Similarly, consider the second example, which involves a call to function foo and has two arguments which involve two expressions, each involving a side effect. The two side effects may proceed in either order or concurrently. The situation where the computation is unordered is also called unsequenced evaluations in C. In this talk, I'm going to show that the unspecified order of evaluation semantics in C increases optimization opportunities for a compiler, and that the speedups can be as high as 2.6x in real-world code. Consider what happens if there are unsequenced evaluations that involve concurrent accesses to the same memory object. Such a situation is not very different from a data race, and we also call it an unsequenced race in our work. To understand unsequenced races, consider the 6 examples on the slide. In the first example, I plus I, there are unsequenced accesses to the same object I, but both accesses are read accesses, and thus this is a legal expression in C. In the second expression, there are two accesses, of which one is an update, but C semantics state that the RHS of an assignment is sequenced before the LHS of the update to the LHS of the assignment, and thus even such an expression is completely legal in C. Now consider expression 3. It involves two side effects on the same variable I, which are unsequenced. This situation and the evaluation of such an expression yields undefined behavior or UB in C. Similarly, expression 4 involves a read and an update to the same object P such that the two operations are unsequenced with respect to each other. Such a situation is also undefined behavior in C. Now consider expression 5. It involves an increment to star p and a decrement to star q during the evaluation of the expression. The two updates to star p and star q are mutually unsequenced, just like expression 3. Now this expression may or may not result in UB depending on whether star p and star q refer to the same object or not. For example, if star p and star q refer to the same object, say I, then this expression would yield undefined behavior. On the other hand, if star p and star q refer to different objects, then this is a legal expression and it would evaluate to a well-defined value. Now consider expression 6. Again, expression 6 has two side effects which are mutually unsequenced. The evaluation of this expression would be well-defined only if aj is known to not alias with I. If aj refers to the same object as I, then the evaluation of this expression would be undefined. To summarize, some expressions exhibit undefined behavior only for specific input values. In the literature, unspecified order of evaluation has been usually considered harmful. For example, C11's OOE semantics contain less non-determinism than C89's. Similarly, C++ semantics for order of evaluation or OOE have been recently determinized significantly as detailed in this 2016 paper. C++17 has significantly less non-determinism than both C++11 and C++3 in the semantics of its order of evaluation of expressions. This is also reflected in compilers because compilers tend to generally ignore the non-determinism present in the order of evaluation semantics of the programming language. Production compilers like GCC, LLVM, and ICC simply choose a deterministic evaluation order at a very early stage of the compilation pipeline, namely IR generation. However, Non-determinism in the evaluation order of expressions was perhaps introduced for a purpose. Consider the expression E1 plus E2. The expression encodes the fact that the evaluation of E1 may proceed concurrently with the evaluation of E2. For example, E1 and E2 may be computed in parallel. This can be done legally even though E1 and E2 may involve side effects and references. Such semantics are especially useful for compilation to parallel computing substrates like FPGAs and GPUs. Even for CPUs, this allows flexibility in instruction scheduling, register allocation, and enables optimizations like vectorization. In our work, we explore this fundamental programming language design trade-off related to order of evaluation of expressions in programming languages. This trade-off needs to carefully balance programming simplicity against parallel performance. We are particularly interested in the order of evaluation semantics of the C programming language, and we are interested in the following questions. What are the additional optimization opportunities enabled by C's order of evaluation semantics and the associated non-determinism? What is the compiler support required to realize this additional optimization opportunity? How commonly are such coding patterns encountered where this optimization opportunity is present? And are the programmers coding such non-determinism correctly, or is it a source of programming errors? We begin with the first question on additional optimization opportunities. Consider this example, min-max, that is supposed to compute the indices of the minimum and the maximum elements in an array A of n elements. The returned indices are supposed to be returned in locations *min and *max. The body of this function initializes *max and *min to 0 and then executes a loop to identify the eventual values of *min and *max. Notice that the initialization of *min and *max is done through an expression that involves two assignments or two side effects, one to *min and another to *max. Also, these two side effects are mutually unsequenced. A regular compiler would convert this expression and choose a deterministic order of evaluation at a very early stage in the pipeline. For example, it may choose to first initialize *min and then initialize *max. Another compiler may choose yet another evaluation order. For example, it may choose *max to initialize *max before initializing *min. In either case, the compiler would have lost some of the information that was present in the original expression. From the original expression, we can infer that this expression would yield undefined behavior if *max and *min refer to the same memory object, as we discussed earlier. Thus, *min and *max must not alias for this evaluation to be well defined. If the compiler can encode this information and maintain it somewhere, then even if it chooses a particular deterministic order, let's say it chooses to first initialize *max and then initialize *min, it would have retained enough information such that it may reorder such computation and also do other things with such information. In this particular case, this information that *min must not alias with *max allows the compiler to register allocate both *min and *max for the entire duration of the function body, including the loop. In this case, this results in a speedup of 1.5x over already optimized code. None of the current production compilers are able to realize this speedup. So what is the compiler support required to realize this optimization opportunity? Consider this expression wi plus equals xij equals I into j. This expression contains multiple sub-expressions such as xij, I into j, and the expression formed by the assignment operator xij equals I into j. All these three sub-expressions that I just mentioned are mutually unsequenced with wi, which means that the evaluation of these expressions can proceed concurrently with the evaluation of the expression wi. Further, one of these expressions, namely the xij equals I into j expression, involves a side effect on xij which is unsequenced with the read on wi. Based on C semantics, this would be undefined behavior if xij and wi were referred to the same object. Thus, we can infer that xij must not alias with wi for the evaluation of this expression to be well defined. Thus, our algorithm involves a bottom-up tree traversal of the expression trees in the C program. At each step in the bottom-up traversal, we identify what operators are used in the expression, and based on the semantics of the operator, infer must-not-alias relationships between different sub-expressions of the expression tree. To get a sense of how many operators involve side effect and are involved in unspecified order of evaluation, there are a total of 47 operators in C, of which 15 involve side effects and 30 are involved in unspecified order of evaluation. Of all the operators in C, the function call operator is special because the bodies of the callee functions may update program memory, and yet these accesses inside the body of the callee function are not considered to race with the other expression references in the expression. Consider this example and the underlined expression foo plus global equals 10. Notice that this expression involves a call to function foo, which in its body also modifies global. Now, this expression has unspecified order of evaluation, which means the assignment may be executed before the call or after the function call. Yet, the evaluation of this expression would not be undefined behavior as per C semantics, because the update to global is not happening in the expression itself but is happening as part of the body of the function call. Thus, while the program may return either 11 or 21 in this case, both would be well-defined results, and this evaluation would not yield undefined behavior. This type of non-determinism creates difficulties for our alias analysis, and we have handled such cases soundly in our paper. A typical compiler is organized as a series of optimization passes. And an optimization pass may require queries like, does wij alias with xi or not? Compilers also typically involve an alias analysis subsystem that responds to such queries. One of the possible responses from the alias analysis subsystem could be may alias, which means wij may alias with xi. Using OOElala support, we are able to identify some must-not-alias relationships, as I just discussed, and thus with OOElala support and appropriate plumbing, the alias analysis subsystem is able to return must-not-alias responses for some of the may alias responses that were appearing earlier. Thus, OOElala is able to convert some of the may alias responses to must-not-alias responses. To evaluate the optimization opportunity presented by inferring these extra must-not-alias relationships, we instrumented some programs in Polybench C that were performance critical and that had some known must-not-alias relationships that were otherwise hidden from the compiler. We added expressions with unsequenced side effects to expose such must-not-alias relationships and compile these programs using OOElala. Because OOElala is able to identify such must-not-alias relationships from such expressions, the compiler was able to perform more optimizations, resulting in speedups of up to 2.6x over already optimized code. How commonly are such coding patterns encountered in real-world code? To evaluate this question, we considered the SPEC CPU 2017 benchmarks. We find that there are on average 5 to 23 expressions per 1,000 lines of code that contain unsequenced side effects. This indicates that programmers are freely programming expressions containing unsequenced side effects in their programs, even when they may not be doing so for better performance. OOElala was able to infer up to 12,000 must-not-alias relationships in these programs. And this resulted in up to 100,000 extra must-not-alias responses. Notice that without OOElala support, these 100,000 responses would have been decided as may alias responses. Are the programmers coding such non-determinism correctly, or is it a source of programming errors? To evaluate this question, we implemented a UB sanitizer as part of the Clang LLVM framework in which OOElala is implemented. This UB sanitizer converts must-not-alias predicates inferred by the OOElala algorithm into runtime checks. For example, if the OOElala algorithm infers that starmin must not alias with starmax, then a runtime check is emitted in the UBSAN mode, which checks that this relationship indeed holds at runtime. This instrumented binary that contains these runtime checks was run on the provided reference inputs with the SPEC CPU 2017 benchmarks, and we found no violations of such must-not-alias relationships. This seems to indicate that programmers are using unspecified order of evaluation correctly in C. To conclude, programmers are using unsequenced expressions with side effects in C freely and correctly, even when they may not be aware of the potential performance benefits. Our work shows that significant speedups are available through exploiting this performance opportunity in C programs. More generally, we think that there is a fundamental PL design trade-off, and we explore this trade-off between programming simplicity and parallel performance quantitatively in our work. While we do this for the C programming language, we think that this requires a separate investigation for every different programming language. We invite you to try OOElala at this URL compiler.ai. Thank you, and I'm happy to take questions.